So here's a little device in which we actually built a small LED on a microwave on a strip line, so that we had no internal, so we had no low input capacitance and low resistance. So the RC time constant was quite small, pixel size was small, and you know the decay time here is basically RC limited, but it's only 40 nanoseconds. Okay, so one can switch these things very rapidly. It is easy to read these things at a very high angle, and one can actually plot that. Okay, and the viewing angle is indeed very high. I mean, you can read it at a very large angle. That's also good, of course. The contrast ratio is excellent. I made the comment yesterday that it's very different, and you know that it's contrast ratio for a liquid crystal display of the kind that you typically have on your telephone is not so great. Here, if we just take the device, the contrast ratio is 45 to 1. The biggest problem, I didn't bring it along, but you know, the biggest problem is the back electrode is metal. So if you look through it, as I showed you yesterday, you look through the ITO, you look through the polymer, and what you see then is this mirror, okay? And that mirror, that metal backing, limits the contrast. In fact, if you take that out in the sunshine, you know, it'll reflect at you, and it's very difficult to see. So but there's a way to get around that. The best way to get around that is to use a circular polarizer, because the circular polarizer, you know, light comes in one way, comes out 90 degrees, and you get a dark background, and that's what you have. That's what you have here. You don't see the mirror at all. There's a circular polarizer in there, so you get a good high contrast from that. You can get almost as well with a neutral density filter, but circular polarizer is very inexpensive and makes it better. We can make devices now that are in this display format at about 15 candelas per amp and about 6% quantum efficiency. In our hands, the operating lifetime is greater than 10,000 hours. Philips, with the same materials, describes 40,000 hours. Okay, what does that mean? Of course, that you have to recharge the battery, but if you continuously charge the battery and you run this device, it will run for somewhere between 10,000 and 40,000 hours before it comes down, before the luminance decreases by a factor of 2. There are slightly more than 8,000 hours in a year. So if you sat on the telephone all day, every day, for 24 hours, you know, with the phone plugged in, you could use it for 1 or 2 years. But of course, no one uses a telephone that way. So basically, the lifetime of the display is sufficiently long that you'll throw the phone away and buy a new one for it. But that's what's required in order to get get such a device into a product. There are two aspects to the degradation. One is that over time, at constant current, these are current-driven devices, right? Put current through, you get light out. Light out is proportional to the current. Over time, at constant current, the luminance will decrease. Okay. So here's an example where we started out at 200 candelas per square meter. This was using accelerated lifetime. I'll tell you about it in a minute, but over a lifetime of order 10,000 hours, dropped to a factor of 2. Okay. Now there's another second feature to the degradation. That is that you start off with a fixed voltage. In this particular case, the initial voltage here was whatever, 2.5 volts. And over this time, the voltage increased dramatically. Okay. That turns out to be a more serious effect, because you'll remember that I said to you, in the application, say in the cell phone, the manufacturer will only give you 7 volts. So if you start out at 5 volts and you go up to 9 volts or whatever, that limits the lifetime. So we really have to, must understand what's going on here and decrease the slope. So this is as you can see, using this polymer that the group at Philips focused on. We call it OC1C10 because there's a 10 carbon chain hooked on it to this oxygen. Typically, in many polymers, one finds that the luminance, as a function of time, has this curious initial increase before it starts to decrease. Okay? But it's not really very well understood, but the feeling is somehow it has to do with an improvement in the interfacial contact, an improvement in the injection. And at room temperature, it's pretty flat over quite a long time, and then you see this decrease, and then it starts to increase, and then it starts, the luminance starts to fall. So you raise the temperature to 50 degrees C, and at 50 degrees C, again, it's almost flat, but for a shorter time, and then it rises and falls, and at 70, etc. Okay? So you see the same phenomena, but the time scale is shortened as you go to higher temperatures. We're looking at the luminance decay rate, and I'm going to plot that luminance decay rate as a function of 1 upon T. So this would be, the time, basically the time it goes to half the lifetime. And you can see, by the way, 2 things here that are quite interesting. It's pretty nearly a straight line, so it's exponentially activated. This is a semi-log plot. And whether you use DC drive or whether you pulse it, as I was describing in these devices where the duty cycle is 1/64th, so you have to pulse it up to 64 times the brightness, doesn't really matter. The lifetime is not sensitive to whether you pulse it or not. I'll show you in a minute. The lifetime is only sensitive to the total charge that goes through the device. Okay? So there's an Arrhenius plot here. The voltage increase that I talked about also is activated. Okay? They're 2 separate processes, and in fact the activation energies are not the same, but they're both activated. So one thinks, maybe oversimplified, of some specific degradation feature, which we'd like to understand, of course. When the lifetime is 10,000 hours, it gets very boring, right? Doing measurements over 10,000 hours. Nobody wants to do that over a year. So you need to have some way to accelerate the degradation so that you can get information about the lifetime in a few days. So the way you do that is you go to 85 degrees C, where the lifetime is now a few hundred hours, and that'll tell you, because you know this activation energy, that will tell you that if you go down to room temperature, it'll be many thousand hours. There's a second way to accelerate the lifetime, and that is to run the device at higher brightness, higher current, okay? So here I'm going to run this device at 4 milliamps per square centimeter. Okay, that'll be fairly low intensity. And again, you see this curious feature. As you turn it on, first the luminance goes up a little bit and then it comes down. And then I double the current, do it again, and of course the brightness is roughly twice as high, and the lifetime is about half as much. This one starts off at 50. Here's whatever, 250 hours. This one starts off higher, but drops off to half at 150 hours. Okay, and when you go to 4 times, then of course you get much brighter. 4 times the brightness, but it falls off to half the lifetime in 50 hours. So higher currents give you shorter lifetime. Higher currents, you're passing more charge through. Okay? And I'm going to show you that it's really charge that matters. And when you plot the same data versus charge, low, same curves, the time to get to half the initial value is exactly the same. Okay? So the lifetime is determined by the total charge through the device. So now we know the rate of decrease of the luminous intensity is proportional to the charge and exponentially activated. Let's look at the voltage increase. Okay, you see the same kind of effect. Here you do it at 25 degrees C, and the slope is modest. If you go to 50 degrees C, it's greater. If you go to 70, it's still greater, etc. Okay, so higher temperatures accelerate this voltage increase, which is limiting the lifetime. Similar behavior at different currents. If you run at low current, you get a modest slope. If you go to higher current, the slope gets bigger and bigger and bigger. I'm integrating the current and replotting the data as a function of charge, all the same. So now I know that the voltage increase is proportional to the charge and exponentially activated. I'd like to go farther, right? I'd like to go at least. I'd like to understand this degradation, and then if I knew what the origin was in a microscopic sense, you know, I could try to improve the chemistry or improve the whatever it is that's going on. So first of all, let's just look at the current density versus operating voltage. By the way, you'll remember, you know, there's a built-in potential of 1.8 volts. So in this particular case, we're plotting the current versus voltage minus the built-in potential. Remember what happens? You raise the voltage till you get to the flat band, and then as you go above the flat band potential, you start to inject current. Okay, so this is plotted as V minus the built-in potential. Here's a log-log plot. We could, and all I really want to show you is that in the beginning, the currents are relatively high with a, roughly speaking, power law dependence here. And after 10,000 hours, the currents have fallen by a lot. I mean, here they've fallen by many orders of magnitude, here by whatever, 2. So, and the power law dependence has gotten more steep. So in a very simple-minded sense, the resistance has gone way up after running the device for 10,000 hours. So either the mobility or there are traps or something has happened to make the resistance much higher. Okay? Now remember that the best efficiency comes, one obtains the best efficiency when you have balanced charge injection, when the injection of electrons and holes is the same. So let's assume, for example, that I started off, I worked very hard, I worked with my chemists, I worked with the interfaces, and I achieved pretty good balance of the electron and hole injection. And then let's suppose that over time, for example, I introduce traps in the electron traps. Then the electron current would be unbalanced. The currents would, the electron and hole currents would no longer be in balance. And then you'd have lower efficiency. Okay? So I want to look for something like this. Okay? I already see here that the resistance has gone way up. That doesn't tell me whether it's electrons or holes or both, but it tells me that something is going on in the bulk of the polymer. Okay? So now let's look at the this voltage increase for a device, regular LED, which is 60 nanometers thick. And you see this slope. Make a thicker one, thicker one. So you see the degradation depends on the thickness. It tells me it's something in the bulk. It's the mobility. resistance is higher. But which is it, electrons or holes? Well, we can take that apart. We can make a hole-only device. I showed you how to do that yesterday. You can make an electron-only device. And the answer is unambiguous. In the case of hole-only device, the voltage doesn't change at all. In the case of an electron-only device, you get this huge slope. So this increase in resistance and this increase in slope comes about because the electron mobility is less than it was when we started, probably because of trapping. In the case of holes only, you can make devices with no voltage increase, and it doesn't really depend on the thickness. If you make a device which is electron-only device, that slope is huge, and if you make the typical device, dual injection device, you get something in between, of course, and the fact that it's dependent on the thickness points your mind to the bulk of the material, not the interface. Okay? Now, I'm not trying to tell you that this is a universal behavior. I'm trying to tell you that in this case, with OC1C10, they did a very serious study, and it lays out, how you might go, how you would approach this problem with another material. Similar things happen in all the materials. Details are going to be different, but one can and one must study the accelerated degradation. One must do that because you need to have a method of accelerating the degradation to actually do the work, and then of course you want to understand the origin of the degradation so that you can eventually make the devices live longer. What's the dependence of the electroluminescence on the thickness? And it has to do here with a number of issues. First thing is that, 5 years ago, you make devices and they're never the same. Here are 15 devices, okay? All made nominally at 900 angstroms of thickness. And what I'm plotting here is the quantum efficiency versus polymer thickness. And in fact, the value of the quantum efficiency is almost identical. Okay? This is outstanding reproducibility, and shows that, yeah, maybe you could actually manufacture a device like this, because if you have that kind of reproducibility, you really got control of the device. There's a surprise here, right? It's not monotonic. It has these interesting oscillations. Okay? And again, if you had a spread of this amount in the results, you wouldn't see this nice oscillatory behavior. But I think it's clear here that these bumps are real. So where do they come from? You've got an oscillator in front of a mirror, right? I've got this metal backing. I've got the cathode. So I've got an oscillator here, the electroluminescent species, chromophore, and it's sitting in front of, 500 angstroms or some distance in front of a mirror. So over here, there's another oscillator in the image charge. And when this one oscillates, this one oscillates. Okay? And the distance apart is relevant because they'll get constructive or destructive interference. So if you take this oscillator and move and imagine making the film thicker or thinner, the image oscillator is also moving, and you get interference. Okay? Actually, this was first recognized long ago by Kuhn, and he published a paper in 1970 where he worked all this out. It's a very nice paper. The oscillations there are very deep. In this case, the oscillations are not quite so deep because I do not have one oscillator in front of the mirror. I have a thickness of 1,000 angstroms, and I have oscillators all the way through. So I have to do an averaging over distance. And that dampens out these oscillations, which would have been very deep, to this form. Okay? But the physics is understood in terms of this nice feature of an oscillator in front of a mirror. Important question. You know, in this material, the quantum efficiency for the photoluminescence is probably 70%. But we don't see that high an efficiency, at least not yet, in the electroluminescence. And the question then is, what is the theoretical limit on the quantum efficiency of the electroluminescence? It depends on the nature of the photoexcitations. So let's suppose that the excitations are strongly bound excitons. It comes back to the discussion of yesterday. But let's look at the limits. I told you yesterday that the singlet binding energy for PPV is very weak. But let's examine the question in a broader sense. So if you had a strong electron-hole binding energy, then you can put the electron and the hole together in a singlet state, or you can put them together in a triplet state. And if you have a triplet state, you can have the triplet this way or this way or this way. Okay, so there are three ways to make a triplet and one way to make a singlet. Okay, so if you bring two electrons together, an electron and a hole together to form an exciton, you can do that in 4 different ways, only one of which is a singlet. Now the triplet states do not radiate to the ground state. That's a forbidden transition because it involves a major change in the spin multiplicity. So if you have a strong electron-hole binding energy, only one out of the 4 possible states will give you electroluminescence, will give you luminescence. When you do photoluminescence, you start with the ground state, schematically, and you promote an electron to the next molecular orbital, so you're automatically in a singlet. Okay? So every photon that's absorbed gives you a singlet excited state and can give you photoluminescence. Okay? So that argument would say, just from the statistics of the singlet and triplet, that the maximum quantum efficiency that you could expect from electroluminescence would be 1/4 of that of the PL. So if you had an 70% quantum efficiency photoluminescent material, you would get at most 15% in the electroluminescence. Then there's another problem, which has to do with the mismatch, the dielectric constant of the polymer being high, so you get a lot of internal reflection. You lose a factor of 2 that way between internal quantum efficiency and external quantum efficiency. And if this were the case, then the maximum external quantum efficiency would be about 7%. And we already have that. Okay, so that would be disappointing if we can't go any higher. On the other hand, if you're just making free electrons and holes, polarons, accepting the fact that there would be lattice distortion around, then you make charges, okay? And they wander around and they come together and they can give you a singlet state and they can give you luminescence. Or they could come together in a triplet state, but if there's no interaction, they just go off and wander around until they find until the weak spin-orbit interaction flips the spin and it comes back again. And this time they interact and give luminescence. It just becomes a dynamical process. But if you have free carriers, free in the sense of very weakly bound, then the electroluminescence can be as large as the photoluminescence. A long time, there were data which were never, in which this never exceeded 1/4 of the photoluminescence. In the last couple of years, this kind of number has been achieved, both at UNIACS, I'll show you some results, and in the group of Richard Friend at Cambridge. Once you've demonstrated greater than 50%, then clearly that's not the point. And so I'm just summarizing that. That's what I said. This number can be quite high for a number of polymers. Since we're not limited by the simple spin statistics, there are two possibilities, both of which could be true. The electron and holes are weakly bound, and in the case of PPV, I showed you yesterday that that's the case. The binding energy is a few times kT. The cross-section for singlet capture is much greater than that for triplet capture. Okay? Think about that for a second, right? If the singlet binding energy is small, then spatially the singlet wave function is very extended. Okay? So that if you have an electron and a hole that come near one another, they can get caught in this extended, weakly bound, but extended singlet exciton. The triplet exciton is very tightly bound. Let's say on one repeat unit. So the cross-section, the probability of getting caught in that, even if it's a high binding energy, is small. They actually showed for a number of polymers that the cross-section for singlet capture is 3 to 4 times greater than that for triplet capture. So we actually know that this is true, and we also know in specific polymers this is true. Okay? So this is good news. Okay? We still do not know what the upper limit is here, but the upper limit perhaps can approach, for the electroluminescence, can approach that for photoluminescence. These are the data where we proved that the quantum efficiency was greater than 50% of the electroluminescence. This is a Nature paper. Again, it's the same paper where the oscillatory behavior was done. 1890 or whatever, when Thomas Edison makes the light bulb, he gets a performance in luminous intensity of approximately 1 lumen per watt. By the way, if you buy a light bulb today, if you go to the store here, I think it's 10 lumens per watt. Yeah, unfiltered incandescent is about 10 lumens per watt. If you buy a halogen lamp, it's 12. If you buy a fluorescent lamp, they're really good. Fluorescent lamps are quite efficient. Okay, a small problem there. There's a lot of mercury in them, and they make for difficulties. But these are conventional light sources. So in 1965, the gallium arsenide LED was discovered. At that time, the efficiency was terrible. Okay, these were red LEDs. The efficiency was 0.1 lumen per watt. And gradually over time, they learned about the limitations and got rid of the defects. And as you can see, gradually, this technology becomes really good. It's good enough, of course, that now stoplights are made with inorganic LEDs, and the backup and the brake lights for automobiles are made. And today, we're up here with those inorganic LEDs, comparable for yellow and red, comparable to even a fluorescent light. Now, just to finish that story, so in 1991, Suji Nakamura discovered or invented the blue gallium nitride LED. And progress there was really fast, as you know. That's now up here and increasing. So here was the discovery, this is Tang and Van Slyke, et cetera. We've got small molecule LEDs discovered in whatever, 85, consistently improving, even higher than this now because of the introduction of phosphorescent, electrophosphorescence into these materials. And here are the polymer LEDs discovered 1990. We're up here now, somewhat higher. So this is an indication of what's happening, both in the case of small molecules and in the case of polymers. You know, these curves they're not vertical, but they're very steep, and there's no expectation that there's no sign of the fact that they've reached the top. And as I just showed you, in the case of the polymer LEDs, we know that this number is still much below the quantum efficiency of the photoluminescence, and we know that we have passed already this 1/4 barrier, so we're not limited by that. So we can expect this to go on up, and that's what's happening. These are luminescent semiconductors. Okay? Now I want you to do the following. Okay? Close your eyes. Come on, close your eyes. Now open them again. These are inks. Okay? These are not just semiconducting polymers. These are inks. I'm going to put them in an inkjet printer. I'm going to spit out picoliters of this ink, and I'm going to print displays. The point is clear. If you could print them, you know, you could have a lower capital investment. You could get rid of a huge fab and reduce the manufacturing material. So the idea is, what you want to do is, you know, in order to make a full color display, you need to have red pixel, blue pixel, green pixel, you know, RGB, RGB. And then you need to address those so that you get the various colors. So that is a real display. This was made by Seiko Epson. It's printed. Here's one that the CDT people like to show, earlier version. If you blow this up, this is a photograph that was taken at Uniax. It's not this one, but it's, you know, it's a similar thing. Here you see the red, the blue, and the green pixels, and they were printed. Okay? And then if you address those pixels in the proper way, you know, so in this region of the display, only the blue one is on. In this region of the display, all three are on, so you get white. If you look at this display a week later, okay, it doesn't look so good. Because the different polymers, the different colors, degrade differently over time. So it looks great now, but in a month from now, it won't look so good. Okay? So in order to make this a commercial product, you have to have all three of the polymers that you're using with very long lifetime, so that in the time that you want to use it as a customer, you do not suffer from, the display does not suffer from differential aging, which would make the colors look funny after a while, right? Your eye is very sensitive, and your demands as a customer are very high. Think about your color television set at home. You know, if it doesn't look perfect, you call the repairman or you buy a new one. So this is very attractive technology, and is a principal reason why a great deal of money is being spent on the polymer LED project, because these are inks. So you can print them. And you can look forward to very low cost, and you can look forward to printing them onto plastic substrates, for example. So let's talk about that. So this is a photograph, obviously, of a flexible a piece of plastic with 1, 2, 3, 4, half a dozen PDA type displays. Now the problem is that as you recall, device is made with a low work function metal in order to give good electron injection. And while you're running the device, you've got electrons in pi star in the pi star band, so they are reactive, and the barium or the calcium is reactive. So you have to package this in a way that does not allow oxygen or water vapor. Plastics are too permeable. Water vapor will come through, oxygen will come through. Okay? Water vapor is particularly bad because water vapor will react with the calcium or barium at the interface. Then your injection is gone, and then the device doesn't work. And of course, the interface is the weak link in this device. So it turns out, you really need a hermetic seal that is nearly perfect. What's being done now, the technology that is being worked on is basically the following. To make a barrier film, take a plastic substrate, buy a good substrate, very, very flat, very uniform. And then what is done is to sputter onto that substrate an inorganic layer. Could be silicon nitride, could be many things, but inorganic layer. If you were able to make that inorganic layer without pinholes, then 200 or 300 angstroms is sufficient to prevent anything from coming through. But you can't do that. There are always pinholes when you do a sputtering like that, and it's worse if you have any structure on the substrate. So it's important to get a very smooth substrate. Okay, so then I put on an inorganic layer, and I know it's going to have pinholes. So then I put on another layer of let's say, polymerizable material, and I polymerize it. Again, a few hundred angstroms. And then I put on another layer of inorganic, and then another layer of polymer, and then another layer and then what I hope is that the pinholes are so few and far apart that the diffusion pathway is, very long. And if it's long enough, then this barrier film will be good enough to, stabilize the degradation. Now, I should comment that often when people talk about these flexible LEDs, the next thing they do is they say, and what we dream of is we're going to have a display like this, and it's going to be all flexible, and I can fold it up and, put it in my pocket and carry it around. And then the next thing we say is, and you realize, of course, that the display is basically the computer, because I can put I can put all the circuitry for the rest of the computer here in a little place, so I can have a computer that I carry around that's cheap and that is flexible, etc. I don't know. What's really important here is that if you have a device, an LED like this that's flexible, and I put it in here and I drop it, it doesn't break. That's what's important. Okay, that's the first thing that's important, because the largest source of failure on, for example, cellular phones and PDAs is because people drop them. And then finally, there's a dream that if you have a flexible technology where the substrate is flexible, you can go roll to roll. Okay, so that you can imagine in your mind a roll of plastic substrate here coming out, going into a bath of polymer, coming out, going around, roll it up, etc. And you've got a continuous process for printing or roll-to-roll manufacturing such devices. So this is far in the future, and I don't know whether it'll come to play, but come to pass. But that's part of the dream of the flexible substrate.